All right, so here's another problem I wanted to go over from the worksheet. I think this is E from activity 4. So we're going to try and figure out whether the reaction will proceed by an SN1 or SN2 mechanism. We're going to predict the products, and I'm also going to draw a general step-by-step mechanism for the reaction. So with this one, all right, so you always want to look at the substrate first, I think. So with this one, even though you see you have an activated nucleophile here, so this is a strong nucleophile. And so even though this is here, you look at the substrate and you say, okay, here's the carbon connected to the halogen, one you always want to look at, because that's the only one that's going to be undergoing any transformations in the reaction. And you see that it's connected to 1, 2, and 3 different carbons. So automatically it's a tertiary substrate. So once you see that something's tertiary, there's no other, it can only do an SN1 reaction because it's going to form a stable carbocation. The mechanism shows you why it's SN1. So the first thing that happens with any SN1 reaction is the spontaneous dissociation of the halide from the alkyl halide to give you a carbocation. Right, so I'm just going to draw this methyl in with the wedge, or with the line bond, because it really doesn't matter what's happening to this methyl group. Only stereochemical changes are going to happen around the carbon that was originally attached to the halide. And so also in the, I'm also going to draw this methyl with the line bond too, because once you form a carbocation, it's a plane, right? So they're all in the same plane. So nothing's really pointing in or out of the page. It's just flat, just like this piece of paper. And now you have the nucleophile that comes into attacks using one of its lone pairs. And that brings you to your product. Now in the product, I'm just going to draw all the line bonds and wedge bonds out, just to signify the distinctions between the products and the reactants. So in one case, once the hydroxyl group makes the attachment, you'll have the product with the hydroxyl group, or the alcohol that results with the same stereochemistry as before. And then you'll also have its enantiomer. And that's going to give you a racemic mixture, because there's equal probability. So once you form the plane, right, it's flat. And the nucleophile can either attack above or below. There's equal probability, in theory, of attack from either side of the molecule. So that's why you get a racemic mixture. So just remember that when you do SN1 reactions. Also, before you even consider stereochemistry at all, make sure you have a chiral center. So if this molecule ended up looking like this, like say we didn't have this methyl group up here and it was just a hydrogen, and you have this thing going on. So say this was your reactant. It really doesn't matter that much that I drew a wedge or dash, or your wedge or dash bonds here, because the symmetry of the molecule makes it such that, you know, these two attachments on either side are equivalent. So there's no way that this carbon is a chiral center. So you can just draw the product out. In that case, you just draw the product out when the hydroxyl comes in. It would just come out. You just draw it like this. And I just left the methyl implicit there. So just make sure you're always thinking about chiral centers before anything else as well.